Hello, everyone, and welcome back to this series of Agentic AI. Today, we'll go through the basics of Agentic AI. In previous video, we've made a shift from generative AI to Agentic AI. We stopped thinking about AI as a model, and we start thinking about it as a system. This shift sounds subtle, but it changes everything that comes afterwards. Most conversations are about AI still revolve about prompts, models, outputs, and so on. But the moment AI systems start to act over time, those ideas are no longer sufficient. In this video, we are not redefining agentic AI. We've done that in the previous one. But we are asking more important question on how do agentic systems behave over time once they are deployed in real world environments, and what structures do they need to stay safe and useful. So it's all about behavior, as we've seen. Um, the definition of agentic AI is not about the intelligence itself. It's more about persistence over time. It's the actions that an agent can take, then observe what happened, and afterwards to decide what to do next. This loop might repeat seconds later, minutes later, days later, and that's where the design over time, the design for behavior over time comes as a necessity, as a requirement. And here we have more questions to appear. What does the system remember? And how the system decides what success look like, and what happens when the environment changes, and what happens when the agent itself fails to achieve what it's supposed to achieve. And so these are like basically not chatbot questions. They are system control. It's about system thinking here. And as you see on this diagram on the right side, so it's yeah, we have the LLM inside as a core component here, but we have the other elements around to have this full control cycle from planning, action, reflection on the action, updating the status, internal status or environment, and then observe what happened and replan according to that, what the agent has learned through this process and what it will take actions afterwards. So basically, this is just to say that um, agents are not LLMs. And this distinction is where many early agentic systems go wrong, actually. A large language model is powerful, but it is fundamentally reactive. It's not, it doesn't track progress in general. And it doesn't know whether it succeeded to do what it was asked to do or not. It just provides us an answer, a response. And it doesn't know if it was correct or wrong. So that output that is generated by the LLM, it is the end. And it's not responsible for anything afterwards. While agents are totally different here. Agents, an agent maintains state, so it's stateful. It remembers what it tried before, and it can compare the current situation to its objective. So it decides what to do next, what would be the next move towards that objective. And this makes the agent more kind of proactive rather than reactive. It maintains its status, it knows what to do next, it decides, actually, not only knows, It decides what to do next, and it knows if it arrives to its final state, which is the objective or the goal of the agent. A useful way to separate these two concepts here, LLMs and agents, is to think about the LLM, the large language model, as the cognition provider, while the agent as the control system. So the LLM is the reasoning engine, while the agent is the control system. And here is cognition is the understanding and reasoning what is requested, and then the control is to sequencing, providing constraints, execution, and feedback. And this whole thing give us this kind of a small or a clear distinction between intelligence and agency, where they are not the same thing. In general, agency emerges from three main capabilities working together, which are autonomy, reasoning, and tool use. Autonomy is the ability for the agent to decide what to do next without constant human intervention or instructions. But autonomy is not a switch; it's a dial, and it ranges. It's a spectrum here. It ranges from different types of actions that can be done. So, for example, some systems will only recommend actions; they don't execute them. Others they execute actions, but within or inside strict constraints, while other agents operate totally independently and escalate only edge cases, for example. Reasoning is what allows the agent to break big goals, big objectives into steps, find options, compare alternatives for each step, and anticipate the consequences of what it has chosen. Then tools is what let agent to search, calculate, run code, query databases, trigger workflows, and so on. Also, tools introduce different or a new set of, let's say, problems related to cost, safety, and risks, and for sure some changes that they made or they can make as they are irreversible in the real world environments. That's why tools must be constrained, logged, and strictly governed. Here's a common misunderstanding between automation and agentic AI, and so let's be careful when we talk about this. There's a lot of dialogue or discussions or narrative out there on automations and tools that provide automations and so on and so forth. But clearly, agentic AI is not a better version of automation. It's not an automation with reasoning. That's totally not the case. Traditional automations assume stability. Inputs are predictable, paths are predefined, failure modes are known and well planned for. While agentic systems assumes uncertainty, they expect ambiguity, they expect partial failure, they expect change in the status, whether in internal status or environment status. That tells us that automation executes scripts, predefined scripts, while agents or agentic systems they adapt at runtime to define what to do next and how to act to it. We will see later in one of those videos a real examples on the differentiation between or distinction between tools and automations and agentic AI, and we'll see how we design for each in general. We've been talking about agentic systems. And what are the types of those agents? In general, we have three main types of agents. First one is single agents, task agents, and these are like just they know what to do. They are narrow and focused. Like for example, we use them when the problem is well defined, success criteria is very clear, and so on. Examples include summarization, classification, structured extraction, short analysis tasks, and so on. So, like we have an input into LLM with tool use and output. So it's so clear to how what we want and how to do it. Second one is multi-agent systems, where tasks are more complex and they benefit from specialization. And here we have different types of agents within the system. For example, when agents do like for general support, as we see on the diagram, another one for to do shopping assistant and hotel booking and flight booking and so on. This is one type of specialization, and other systems, multi-agent systems, will be more kind of having one agent to do research, another one to do the plan, third one to do critique, and a fourth one to execute. So different types of multi-agent systems that we can see there. The third one is agentic workflow, and here when the workflow agents orchestrate and manage dependencies. They enforce the order and they track progress. In general, as we see on this simple workflow here, we have different agents. They are colored the same way, so they are probably not different, but they can be different. As we said in the previous type in the multi-agent systems, they are more or less close to each other. The distinction is that in the multi-agent systems here, the task can be executed by only one type of by one agent that use different other types of agents, while in the workflow it means it's more complex and on the routing and the decision nodes on the workflow itself. And we will see that in practice in the coming videos. Now we arrive to agentic design patterns. These patterns are reusable system level solutions uh, to some challenges that we have been facing in the agentic design in general. So, although this domain is new, but there has been some research and some patterns has been kind of popping up, and there were some classification of these patterns, and now we are working on them as kind of standard, semi-standard design patterns. They are proven ways of organizing behavior. They are not model prompts. They are independent from tools, from framework or specific architectures. They are not related to the internal components of the language model or tools, etc. But they are the ways we organize the work. And each pattern of them is a response to a challenge. For example, we need them to, because agents are continuously acting not in a single turn, so there are some patterns to handle such issue, because the behavior emerges over time, not at what decision point. Complexity grows faster than linearly. Autonomy requires explicit control structures. Safety, cost, quality must be engineered. System must remain observable and governable, and so on. So these are type of problems or issues that we have seen in the short time of agentic AI lifetime so far, and there are some design patterns that are used to overcome these challenges. We will go through these design patterns just in a quick overview for now, and I will provide a link to a very good book actually on these design patterns, where I got this classification from. And there's actually another video that I will provide the link to in on YouTube as well, and it goes through these design patterns in very much detail. So I'll just provide an overview here, and if you are interested in learning more about it, you can follow the links to those to the book or to the other video. So let's start with the first type of design patterns or first group. They are the first family is about structuring work. They are about prompt chaining, planning, parallelization, and so on. We use these design patterns when tasks are multi steps, error prone, and or too large for a single pass. Um, we use prompt chaining when you need the intermediate checkpoints. For example, drafting a report, validating claims, or rewriting for clarity. We use planning when tasks as dependencies. For example, building a feature that needs requirements and architectures and implementations and tests, etc. Parallelization when subtasks are independent. For example, summarizing 10 documents and this at the same time then merging a unified synthesis and so on. In general, for this family of design patterns, they are more reliable. They provide more reliable outputs. They are more debuggable. They can be debugged more easily, and we have a clear intermediate artifacts. While at the same time, on the other hand, they increase latency, they require more orchestration, and there are a risk of context explosion if we carry everything forward. Moving to the second type of patterns or second family is decision and control, and that includes routing, prioritization, and goal monitoring. Uh, we use routing when requests vary widely and different specialists are needed. Let's think about customer support, like for example, for billing, technical help, account access, and so on. We use prioritization when resources are limited and urgency varies. For example, similar to the triage, what must happen now versus later. And monitoring, we use it when we have long running objectives, for example, and this matters when the agent must detect drift and correct the course, for example. In general, they provide efficiency and focus, better use when of specialized agents and tools here, and they scale better than single agent or single generalist agent. On the con side, misrouting is very costly. We need to pay attention to misrouting, as their rigid goals can reduce adaptability, and they require confidence checks and fallback. The third family of design patterns is the family that protects quality in general, and that is about reflection, evaluation, exception handling, and so on. We use them, for example, the reflection when quality matters, and we need and we can afford revision loops, for example. For example, policy writing, high stake emails, or any content where errors are expensive. We use evaluation and monitoring when the systems run continuously at or at scale, and that's where drift and regression show up. We use exception handling whenever failure must not cascade, and especially in tool heavy systems. On the pros side, they provide increased trust and consistency. They detect drift and silent failures early on, and they reduce cascading errors. That's very, very good. But on the con side, we have more cost and more latency in the system, infrastructure overhead, and the risk of alert fatigue if monitoring is too noisy. The last family of design patterns, uh, it's about scale, safety, and cost. And this family is what happens when the systems act as or appear as at scale. We have coordination, safety, and cost. Multi-agent collaboration helps when multiple perspectives are needed. Human in the loop becomes essential when decisions are high stakes. Guardrails and tool governance matter whenever tools can cause harm. Resource-aware optimization matters when cost scale with volume and so on. These patterns are enable enterprise-grade systems, but they demand disciplined engineering in general. There are other type of agents that are related to knowledge, memory and learning, memory retrieval, and so on. uh, these types we will see more of them in the general style and in the general agents that we will design with RAG, with memory management, with context management, and so on and so forth. One important thing when we talk about agents and design patterns, uh, do not stack patterns, do not overuse the patterns, because these patterns are there to help solve some challenges, but we don't overstack them on top of each other and overuse them, because they are not for that, because every patterns add cost, add more risk sometimes, and so on. Let's always think about our agentic system as simple as possible and as governable as possible. This is the kind of the edges where we think about the systems. So the design patterns are there to help us, but not to complicate our design. We don't use them just for the sake of using design patterns. Uh, you see, we have in this video we've covered the basic element of agentic AI. We have moved from definitions to system behavior, more or less, and we've worked a little bit on the distinction and moving from LLMs towards agents. What is autonomy, what's reasoning, what's tool use, and so on. And that we covered a little bit of the design patterns just to set the ground for what comes next as we move towards the core components of agentic AI on intent understanding, reasoning engine, memory systems, and tool use and APIs. And this is really important to see here, as we will be start using a little bit of technical stuff there. We will start using LangChain as a framework to explain a little bit how we can build these components into our agents, starting from simple agents, and we will build up and up until having a full agentic system as we move forward. So from the next video, we'll start seeing some code in the videos, but it will be light touch code. It will not be heavy code. So you can still continue if you are not a technical or you don't have a technical background. You can continue watching these videos and benefit from the like theory or the information that are there. And we will start to see a little bit of a code in the coming videos. So this is what's coming next for us. We are looking at the in 4 videos actually, in intent understanding, reasoning and planning, memory and state, and tool use and executions. That's all for today's video. And as usual, thank you so much for your time and attention, and see you in the next one.